Hello everyone. So welcome to the second video of the basics of Thyristor. So today we are going to learn about different voltage ratings of the Thyristor. So there are five or six types of different voltage ratings. So let's name it. So first is VDWM, VRRM, VRWM, VDRM, VDSM, VRSM. Okay. So here, as you can see, the VDWM, VRWM are mirror image of each other. VDRM, VRRM are the mirror images of each other. VDSM and VRSM are the mirror images of each other. Okay. So let me go into presentation mode maybe. Yeah. So this VDWM or VRWM are the forward and the reverse voltage of the sine wave that is passing through the thyristor, or the sine wave of the source. Okay. So let's imagine the thyristor is connected to a particular type of three phase source or single phase source, and the single phase source is having a phase voltage or line to line voltage, let's say line to line voltage. So it has a line to line voltage of, let's say, 100 volts. So the peak voltage will be 142 volts. Okay, root 2 into 100. So VDWM or VRWM will be 142 volts for the particular thyristor, and this VDRM or VRRM is the peak transient repetitive voltages in the forward direction or in the reverse direction. Okay, so when does this occur? This occurs when there is a transient or periodic transient in the thyristor operation. So when can it happen? Generally during the turn of process is the main culprit for these two types of voltages. Okay, and the third is VDSM and VRSM. The VDSM and the VRSM are the peak surge voltages, okay, that is non-repetitive in nature. Okay, and generally the VDSM is 130 times of VDRM, and VRSM is 130 times of VRRM. Okay, and since these are non-repetitive, this doesn't occur frequently, but these are not a kind of avalanche of a thyristor, or this, due to this there will be no damage to the thyristor. Okay, and this will be always less than VBO, the for breakover voltage. So VDSM will be less than the forward breakover voltage, and VRSM will be less than the reverse breakover voltage. Okay, similarly there will be two other terms. One is the VT and one will be your dV/dt term. Okay, so VT is the minimum voltage that appears across the thyristor, or that is the on state voltage drop of the thyristor. Okay, when the thyristor is in conduction state, and this VT will depend upon the current flowing through the thyristor as well, as we discussed yesterday. So the formula for VT will be VT naught, the minimum forward voltage of the thyristor, VT naught plus ID, the current flowing through the thyristor, multiplied with RT, the resistance, thyristor resistance or on state resistance. Okay, and this gives your actual voltage drop of the thyristor during a particular amount of current passing through it. Okay, and we take that as an average current value. So these are few voltage terminologies that is related to a thyristor or any thyristor. It's not about any particular thyristor, it's a generic statement about all the thyristors. Okay, now let's see what are the current ratings of the thyristors. So I'll come to the latching and holding current, but before that there are few other current ratings of the thyristor, such as maximum average current and the RMS current. Okay, so ITAV, or the maximum average current, is the maximum amount of the mean value of the current that can be flown through the thyristor, and the RMS is related to more of the heating nature of the thyristor. Okay, and here we have two other types of current rating. One is latching current and one is holding current. So as the name suggests, right? So latching and holding. Latching means to latch on something. Okay. So here, once the thyristor current crosses, or the forward current through from anode to cathode crosses a particular value of current called latching current, then only the thyristor can be turned on. If the current value doesn't cross this latching current, and when you remove the gate pulse, okay, so first of all, the latching current can occur across the thyristor once you provide a gate pulse. Okay, so once you provide a gate pulse and the current start increasing, okay, but the current doesn't reach latching current value or that level, and you remove the gate pulse prior to reaching the latching current level, then what happens is the thyristor again goes back to non-conduction state or off state. Okay, so we can say the thyristor is not fully turned on. Okay, so for proper turning off, for proper turning on of the thyristor, the forward current of the thyristor should go beyond the latching current value. Okay, similarly, during the turn off process of the thyristor current should go below the holding current value to reach to a particular to reach to a properly turn off state. Okay, so once the current through the thyristor goes below the holding current after gate pulse removal, okay, and this the change of current, okay, below the holding current can happen due to the natural commutation or the force commutation. Okay, so since we will deal with the thyristor converters, we will only see the natural commutation as of now. Okay, so as we know, the natural commutation is the commutation from the source, okay, due to the source voltage. So the source voltage is responsible to make the thyristor turn off and to make sure that the thyristor is properly turned off. Okay, so these are a few current parameters, and some additional current parameters are the I square T rating, which is the minimum fuse rating required for the thyristor protection. Okay, and some ratings such as DIDT rating, the maximum DIDT allowed through a thyristor. Okay, so we understood what is the voltage rating and what is the current ratings, what are the voltage rating and what are the current ratings of the thyristor. Okay, and now we'll proceed to see some examples or some numericals how to calculate the latching and holding current and some other parameters of the thyristor. Okay, some basic numericals, and then we'll proceed to some simulations. Okay, let's do some calculations on a problem for the latching current. Okay, so as we understood The latching current is the current related to the turning on of the thyristor. Okay, so in this problem, the thyristor is gated with a pulse width of 40 microseconds. The latching current of the thyristor is 36 milliamps. Okay, this is the required latching current for a load of 60 ohms and 2 henries. Will the thyristor get turned on? Check if the answer is negative. How this difficulty can be overcome for a given load. Find the maximum value of the remedial parameter shown dotted. Okay. So what is the, first of all, let's understand the problem completely. So we have a source voltage of 300 volts, and this is the DC voltage, and a thyristor switch is there, and the load is 60 ohms and 2 henries. Okay, so the latching current of the thyristor is 36 milliamps. So whether the thyristor will be able to completely turn on if a gating signal of a pulse width of 40 microseconds is given to it. Okay, so let's see how to proceed in this problem. Okay, so as we know, the particular equation for the for any RL circuit is this. Okay, this is the current and voltage relationship of a RL circuit. Okay, so IT is equal to Vs divided by R whole multiplied with 1 minus e to the power minus t by tau, or minus R by L into t. Okay, so here IT is equals to Vs 300 volts divided by the load R 60 ohms, 1 minus 60 by 2 multiplied with 40 microseconds, it's given over here. Okay, 40 microseconds, hence it is coming as 5.996 milliamps, 5.996 milliamps. Okay, so in 40 microseconds the thyristor current will reach only 5.996 milliamps. Okay, and the latching current of the thyristor is given as 36 milliamps. Okay, so what we understood is the thyristor will not turn on, okay, if 40-second pulse is given to it. Okay, so what we can do is either we can extend the pulse width, okay, or we can add a additional parameter in parallel to this. Okay, so what will happen when you add an additional parameter? Okay, so basically what you are doing is, the in this figure the remedial parameter will be a resistance, let's say resistance R1, because current can rise in resistance without any time delay. Okay, the value of the Ri or R1 can be obtained as IT is equal to 36 into 10 to the power minus 3. Okay, how it came? It is already given over here. 36 milliamps equals to 300 is the source voltage. Okay, this is simple current division rule. 300 by R1 plus the same 300 by 60 into 1 minus T by tau. Okay, so R1 equals to 9.998 kilo ohms. Okay, so if the actual load or the original load is connected with a close to 10 kiloamps of resistance in parallel, the thyristor current will reach will reach the value of latching current within 40 microseconds, and the thyristor will be properly turned on. Okay, so guys, today we have learned about the voltage ratings of the thyristors, the current ratings of the thyristors, and basic example of a of a way of calculation for the latching current. Okay, and in the next video we can do some simulations on the basis of this, and next we'll proceed towards learning the different types of further concepts or further knowledge of the thyristors, okay, in thyristor domain. So maybe we can do a simulation related to this example, taking a non-ideal thyristor or the parameters of the actual thyristor into the circuit, and then we can see how the latching current looks like and what is the turn on and turn off methods of the thyristors, and when we do some turning on and turning off, how does the current and voltage waveform looks like, okay. And also we can see some numericals and some concepts related to the power loss calculation of the thyristor, okay, which will give us the complete idea about uh, the thyristor, the on state and off state losses, okay. And later we'll see some calculations related to RC snubber for the thyristor protection, okay. Thank you for viewing this video. Bye bye.